In this particular video, I'm going to be doing a short review over sections 7.2 and 7.3, simplifying radical expressions. We're going to be simplifying radical expressions, including those with variables. And when we do so, we're going to assume that all of our variables are positive. We're also going to be doing binomial radical expressions as well as rationalizing denominators. Okay, so the first thing we're going to start out with is just simply simplifying a radical expression. I've got a few different examples here that I'm going to work out for you. The first one being the square root of 108, x to the 5th, y to the 12th. Now in this particular problem, and any problem like this, we're going to break this into the individual pieces. So we're going to do the square root of 108, we're going to do the square root of x to the 5th, and the square root of y to the 12th. So when I work out this problem, the first thing I'm going to start with is the square root of 108. Okay, then another part of my problem is going to be the square root of x to the 5th, and then another part of my problem is going to be the square root of y to the 12th. Okay, so with the 108, 108 is not a perfect square, so I'm going to check my list of perfect squares over here, and I'm going to figure out if there are any of these that would go into 108. And if I do so, I end up with 36 as the largest perfect square that I can get out of 108. 36 times 3 actually makes 108. So when I square root 36, I actually just get 6, and the 3 doesn't square root, so I just get 6 square root 3. Now, for the x to the 5th part, remember when you're dealing with variables, a perfect square is something times itself. So in other words, in a square root situation, it takes a pair of x's to make x to the 5th. Okay, well, if you think of it in terms of perfect squares, x to the 4th would be the biggest perfect square I could get out of that, with an x left here, right? X to the 4th is 2 pairs of x's, so x to the 4th gives me x squared, and I'm left with the square root of x. Now, y to the 12th, the nice thing about y to the 12th is that it actually is a perfect square. You can make an even number of pairs. You can make 6 pairs out of y to the 12th, so when I square root y to the 12th, I actually get y to the 6th. Now, once we have all the pieces done, let's put them all back together. So I put my outside of the radical parts here, so 6x squared y to the 6th, and then inside the radical I still have left a 3 and an x. So my final answer looks like this. Okay, so now let's move on to the second example. This time I'm doing a cube root, same process, just dealing with perfect cubes instead of perfect squares. So I'll be checking out this list of perfect cubes for my 250, which you'll see 250 is not on the list. Largest perfect cube that's going to go into 250 is 125. So when I separate out my individual pieces, it's the cube root of 250, and we're also going to have to do the cube root of x to the 8th. So let's start with our cube root of 250. In 250, we said 125 is the biggest perfect cube that goes into 250, and that goes in there 2 times. So one cube root of 125 is going to give me 5, and I'm still going to have the cube root of 2. Now, as far as x to the 8th goes, when we talk about variables, we're doing perfect cubes. This time I need groups of 3, or something that works in groups of 3. So as far as variables go, for a perfect cube, I'm going to have x to the 6th, but then I'm going to have x squared left over. That's not big enough to make a perfect cube. So in this case, the cube root of x to the 6th is x squared, and I'm also still going to have a cube root of x squared left over. So when I put everything together for my final answer, on the outside of my radical, I have a 5, and I have an x squared. And on the inside of my radical, making sure that I actually show that this is a cube root, not a square root, I still have a 2 and an x squared. Okay, so this is my final answer once I put everything together. Now on this third example, to make this easier for us, rather than simplifying, multiplying, and simplifying again, we're just going to multiply once and simplify once. So we're going to multiply this together. 40x cubed times 5x to the 7th, y to the 3rd. So 40 times 5 is going to give me 200. X to the 3rd times x to the 7th is x to the 10th, and then y to the 3rd. Okay, now I'm ready to divide those into their little parts here. So we square root of 200, square root of x to the 10th, and square root of y to the third. All right, let's do the square root of 200. Biggest perfect square that goes into 200 is 100, so that becomes 10 square root 2. Square root of x to the 10th, again, remember perfect squares would be pairs of numbers. I can actually get 5 whole pairs out of that, so that's a perfect square. And then for y to the third, I can actually get one pair, right? I can get a y squared and a y, and when I square root y squared, I just get y square root y. So when I'm all finished, on the outside of my radical is a 10, an x to the 5th, and a y. And then inside my radical, I still have left a 2 and a single y, like this. Okay? All right, let's move on to binomial radical expressions. Now, again, this time we don't have any variables in here to worry about at this point, but we're going to need to simplify our radicals. And before I do anything as far as combining like terms, I want to make sure that all my radicals are in simplest form. So when I look at my first example here, the square root of 32 and the square root of 98, those need to be simplified before I decide if these are like terms that can be combined. So let's do the 32 first. Whoops, apologize for that. So for the 32, we've got perfect square that goes into 32 would be 16 and 2, which makes that 4 square root 2. Now I already had a 3 outside here, so 3 times 4, that's going to make that 12 square root 2. Okay, now for the 98, perfect square that goes into 98 would be 49 times 2, which makes 7 square root 2. Okay, that's supposed to be a 7 there. And so plus 7 square root 2. All right, when I combine them together, now they look like terms. So I have 12 square root 2 and 7 square root 2 are actually going to give me 19 square root 2 for my final answer. Okay, now the next example, I'm doing a multiplication here. I'm actually multiplying 2 binomials together. And so what this means is I'm going to be using FOIL, my distributive property, to multiply them together. So I start with the first terms, that'd be 5 and 3, that makes 15. Then the outside terms, which would be the 5 and the minus 2 square root 6. So I can multiply the negative 2 and the positive 5 and get negative 10 square root 6. Then the next two terms would be the inside terms. That's the square root of 6 times 3. So that's going to make plus 3 square root 6. And then lastly, I multiply the last terms, which is the square root of 6 times a negative 2 square root 6, which is actually going to give me minus 2 square root 36. Now, if I do some simplifying here first, the first thing I know is that the square root of 36 is actually just going to be 6. And if I simplify even more, 2 times 6 gives me 12. So that's actually going to be a minus 12 at the end. And when I combine like terms, 15 minus 12, right, is going to give me 3. And then negative 10 square root 6 plus 3 square root 6 is going to give me a negative 7 square root 6. And since my square root of 6 is not a radical that simplifies, this is my final answer. Now on the last one, I put this one on here just because sometimes we forget that if it's not a binomial and a binomial, we don't need to do FOIL, we just need to simply distribute. So when I distribute this, 9 times 2 is just simply going to give me 18. And when I multiply 9 times 5 square root of 3, I'm going to get 45 square root 3. And then there are no like terms, so this is all I would have for my answer. So when you have just a simple distributing problem, don't make it more complicated than you need to, right? You just do the distributing, combine anything that combines, and you're finished. All right, so last thing, we're going to rationalize some denominators. Now, when you rationalize a denominator, like it says, is that you just simply need your denominator to be rational. If it cancels out, if it simplifies out, that's great, but if it doesn't, that's fine as long as it's rational. Now, when I look at my first example, it's the square root of 9y squared. If I can rationalize my denominator by simply just doing the square root, I will. So like on 9y squared, if I want to rationalize this denominator, 9y squared is a perfect square. So all I have to do is do the square root of 9y squared, which is 3y. Now for the numerator, I have the square root of 48x. I do want to check and see if that simplifies, and I can simplify a little bit. The square root of 48 is actually going to simplify. 48 can be split up as 16 times 3, so I end up with 4 square root 3. And then the x doesn't do anything, so it's going to stay there with my 3 under my radical. So when I'm finished, although I did have to simplify my numerator a little bit here, this is my denominator rationalized. I didn't have to change anything. It was just needed to be simplified. Now in the next problem, that doesn't work. If you look at the next problem, the denominator is the square root of 5, and I can't square root the 5. It's not a perfect square. So what I'm going to do is try to make it one. And one of the easiest ways to make it a perfect square is just multiply it by itself. Doesn't have to be that way, but in my case, 5 times 5 is going to make me 25. And any rule of fractions says that if you're going to change your denominator by multiplying, you do the same to the numerator. So my new numerator is the square root of 10x, and my new denominator is the square root of 25. And when I get ready to simplify, the square root of 10x, 10x does not simplify. There's no perfect squares in there. But the square root of 25 actually becomes 5. And so now my denominator is rational, and that's all I needed. Okay, it just said to rationalize. There's nothing else I can do there. Now, rationalizing when you have addition or subtraction is a little bit trickier, because if you just use the radical, you're not going to get that to eliminate. It's not going to cancel itself out. So what we use here is we use a conjugate. So if my denominator says that it's 1 plus the square root of 2, the conjugate of that is 1 minus the square root of 2. And same rule applies. Whatever I do to the denominator, I do the same thing, to my numerator. Okay? Now, in my numerator, I have 6 times that binomial. That's just simply a distributing problem. That's 6 minus 6 square root 2, right? All I did is just distribute that to those two things. Now, for the bottom, the denominator, I'm going to have to do FOIL. Okay, so I'm actually going to come down here and write this out and do this 1 plus the square root of 2 and 1 minus the square root of 2. All right, so when I do FOIL, 1 times 1 gives me 1, and 1 times a negative square root of 2 is negative square root of 2. And 2 times square root of 2 times 1 is plus square root of 2. And the square root of 2 times a minus square root of 2 is minus the square root of 4. Okay, well that's 2. And this cancel each other out, so 1 minus 2 gives me a negative 1. So my denominator ends up being negative 1. And like any other fraction, you want to check and see if you can reduce, which this one you can. Negative 1 can go into 6, and negative 1 can go into negative 6, and I end up with this. I end up with no denominator left, and I just get negative 6 plus 6 square root 2, and I'm finished. Okay, so that's essentially everything from sections 7.2 and 7.3 that we looked at in this chapter.